Hello and welcome to today's webinar. In this webinar I will be talking about analysis and design. In analysis I will talk mainly about the dynamic analysis and the process needed to complete this successfully, and then I'll also look at wall distributed reactions and how the output for meshed walls has improved. For the design topics I'll be talking about the three design topics shown in the list. Patterning of eccentricity moments from steel beams on steel columns, minimum design forces, and pile punching check between the piles and the mat foundations. The first feature we'll be looking at under analysis is the dynamic analysis. So this is used for tall and unusual structures. This can be used to easily provide vibration data to wind tunnel testing consultants. First order modal analysis, or previously first order vibrations as it was called in early versions of the program, has always existed within the program. However, the steps required to successfully perform a first order modal analysis were located in different parts of the program. You had to manually create the combinations, or the combination. You also had to remember to set the type of combination correctly. The analysis had to be performed separately, and also result output was separate from the input and the process. Now all the inputs, analysis process, and output can be found in the same place. This allows for easy creation and rapid output because of the more simplified process. To find dynamic analysis, the way to do that is to click on the Analyze ribbon and click on the wind tunnel icon. What this will do is it will activate a new ribbon called Wind Tunnel Data, where all the input, analysis process, and output can be located. So, in this example, we have a reinforced concrete flat slab tower. In this tower, the load includes only the self-weight, which are automatically generated for both the members and the slabs. We've also got some dead loads, or additional dead loads applied, as you can see on screen now, and additional imposed loads too. So the difference between using the dynamic analysis or the wind tunnel data, the wind tunnel method that I'm showing now from the previous method, is that with the previous method, which I'll demonstrate first, it was a very straightforward process. The way to do that would be to firstly build your model and apply the load. Make sure your model's correct and it's stable before performing a vibration analysis. We'd go on into our load ribbon, into our combinations window, and what we would need to do is we would need to create a combination. Now I'm just going to call this modal mass 1, and importantly we'd need to change the class of the combination from gravity to modal mass. We can then go into the modal mass combination, include our loads, so we'll include 100% of the effects of the dead loads and 1/10 of the imposed loads. Over here along the top, and what we'd need to do is we need to go into the applied mass tab, and we'd need to determine the direction which our applied mass is going to be in, and we only want to consider our horizontal loads. So in this case we would untick direction Z, so directions 1 and 2 being horizontal. We would then click OK, and that would complete the modelling and the modelling side, loading and combinations. To perform the analysis, the way we would do that is, I'm just going to turn off the load case there. We'd go into the Analyze ribbon and select First Order Modal, or this was called First Order Vibration in older versions of the program. We would then perform a First Order Modal analysis, and so once it's complete, we can then review the results. We'd need to first ensure that we have the correct analysis method set in this drop-down, which is First Order Modal. I can then select the combination that I'm wanting to review, so in this case it's Modal Mass 1. And if I want to see the displaced shape, what I can do is I can see the displaced shape simply by turning on the deflections, and I can use the deflections slider over here to increase the scale of the displaced shape. The mode or the frequency that this shape is given for can be found in this drop down over here under mode, and the first 10 modes are given by default. The reason that 10 modes are given, we can see if we go into the Analyze ribbon and click on Settings and select First Order Modal. Over here, the number of modes, the default value is set to 10. So what will happen is the program will automatically stop after the analysis after the 10th mode has been found. What we can also do is, which is quite beneficial, is we can also right click and select Animate, and what this will do is it will just animate the displaced shape. So it's helpful to see the effect of how the results are displaced. In terms of output, the way to see the output within the program in tabular form would be to click on the Analyze ribbon again and select this option over here, which is called Model and Results. So in older versions of the program it was called Tabular Data. We'd click on this option over here and we'd need to firstly select the correct analysis type, which is First Order Modal. And using the view type over here, we can select the view type that we want to view. So we can turn on things like summed mass, dynamic masses, we can view things like total masses by level. For total masses by level, we will need to select a combination, and here it gives us the total mass, the dynamic masses. And importantly, in 2020, it also works out the center of gravity, the center of mass at each level, and the mass moment of inertia. So in previous versions of the program, these results here were not given. So some of these tables will have had to have been exported to Excel or exported to any other third-party program, and the center of masses and the mass moment of inertias would have been you would have had to calculate manually. So in terms of performing a first order modal analysis, the modal analysis process is very simple using the older method. However, the issue is that there are many steps, and when you have many steps, chances are you will occasionally forget to perform a single step. What I'll now do is I'm just going to close off this table here. I'm also going to delete this combination that I've created before. And what that will do is it will clear the results. I'll show the new method now of how this is done. And this is all done under the Analyze ribbon by clicking on the wind tunnel icon. When you click on this icon, what this will do is it will now activate a new tab at the top called the wind tunnel data. And within this tab, the steps needed to perform an analysis and view the results and even export the results are found within this new ribbon. I can start by selecting this first icon over here, the add icon, which will take us to the combinations window, and it will automatically take us into a combination where we can see that the dead loads are automatically included. We do have the option of including the imposed load as well. Again, I'll set that to a 10th. We can define the name of the combination again. I'll just give this a slightly different name. Previously, I called the combination modal mass 1. I'll call it modal mass 2 in this case. I'll set the direction, again, as I did before. So turning off direction Z, so we're only considering the horizontal effects. If I click on OK now, it then displays the tabular results for modal mass by level. All the results are currently now 0 because we haven't performed an analysis. We can run the modal analysis simply by clicking on this icon over here, which is Run Modal Analysis. What this will do is it will now display the results for the modal mass combination that I've created and any other modal mass combination you have in your model, and it will also display the results. Now, the important results are all displayed over here, so this is similar to when we were looking at model and results data when we turned on the first order modal analysis results. It's the same table as it was before. The only thing is the tables are now found over here under view type. We can select the modal frequencies, which shows the mode numbers for the first 10 modes, their associated period, and the frequencies also calculated from there. Other outputs, things like mass participation and the modal mass from under each one of these frequencies, are then also calculated. We can also click on mode shape by level, and again this is also affected by the number of combinations that you have, and this is simply just a tabular view of the mode shape per level per mode. So what you'd need to do if you want to see the results for a different mode is from this drop down menu you can simply select a different mode and you can see the difference in mode shape. You can create the full exported output using any of these two icons over here at the top. So they're both Excel icons. The first will just simply export the view that you're currently looking at, and if you want to export the full results you can just simply click on Export Full Report, and this will open Excel or any other XLS viewer and the results will be displayed. Here you can see how the results are displayed. So all the results are displayed in these tables over here, and the results that you're looking at or the type of results you're looking at can all be found in these tabs at the bottom. So here are the different modes, for example, modal frequencies and total mass by level. Equally, what you can do is you can go into the 3D view and you can also view the results for the first order modal analysis in the same way. So you can view the graphical results over here as well. And as you can see, because the input data was the same, even though it was created using a different method, the results are the same as they were before. So the next subject is covering the final new feature under analysis, which is wall distributed reactions. So wall distributing reactions are basically continuous reactions along the effective chord at the bottom of the wall. And these are applicable to the vertical components of the wall reactions at the bottom horizontal. So if you have any sort of sloped bottom, unfortunately, this feature won't be useful there, as it only applies to horizontal levels at the bottom. This is only applicable to self-supporting walls. So if you have a wall supported by a transfer member or a raft or mat foundation, this won't apply. And the results are derived from basic elastic theory used to calculate the stress unit length based on the total moment and vertical force acting at the centroid of the reaction line. So here is another model. This is similar to the one that we had before. The only difference is instead of having columns at the corner over here, we have a wall instead. And that's modelled using a meshed shear wall. In this model, we have a series of wind load cases created using the wind modeler. And what we're going to do is we're just going to run the analysis for those wind load cases. In fact, I'll only run to wind 90 as wind 90 is applying in the positive Y, which will act on this wall here as well. So once the analysis is complete, you will be taken through to the solver view. And previously, when it came to looking at support reactions, I'm just going to be looking at the vertical reactions. The reactions you would see looked something like that, where you would see a series of reactions that did make sense if they were reviewed closely. However, from a distance, they did look difficult to interpret. I mean, you could turn on reactions over here, and what you'd see is you'd see that you are seeing uplift on this side over here, and you're seeing this other side is going into compression. In the middle, you're neither here nor there. The forces are a lot smaller than they are on the edges. Feature we have now is if I just turn off the 2D reactions, is there's now this icon over here which is looking at distributed wall reactions, where what it will do is it will just give you a simplified reaction of what the reaction under this wall here would look like. This here is much easier to interpret than the 2D reactions. If I were to go into the base level and turn on the reactions for this level, again, interested only in the distributed reactions, you can see what the reactions look like for wind 90. What we can now do, what we couldn't do previously, is we can now export those wall reactions to a foundation reactions drawing. And to do that, if we go into the draw ribbon, click on the drawing settings, under our options for our planar drawings, and I'll just expand that a bit, foundation reactions, under walls, we now have this option over here as to how we'd like to view our distributed reactions. So whether you'd like to show them or not is just simply controlled by this tick box over here. And the type of vertical reactions that you can see are also shown over here. So we can see the distributed maximums or distributed extremes. In this case, because we are seeing a push-pull effect, where one side is in tension and the other's in compression for one of the walls, I'm just going to select distributed extremes. If I click OK there, I can now click to create my foundation reactions drawings. And we are then presented with this window. I can now click on OK. And what this will do is it will open up a window which will allow me to see the reactions in drawing form. So this will use whatever you have as your default DXF viewer. We can see the individual walls referenced, and looking at this table over here, we can see the distributed wall reactions. I will now talk about some of the design enhancements and new features. The first being a new feature, which are eccentricity patterns. This is when steel columns are supporting simply supported beams subject to imposed loads. What would happen is you would see an eccentric load applied from the steel beam onto the column. If you had columns supporting beams on all four sides, what you'd see is those eccentric effects on all four sides. Now, what you can do is you can apply patterns to the eccentricity loads from beams. The patterns are as follows. Here you've got a column with four faces, so faces A and C being the flanges, and faces B and D being the web. Initially what the program did was if you had beams supported on all four sides like this over here where you see the ticks, what it would do is it would just simply sum up the eccentricity load in the major axis and sum them up in the minor axis, or it will calculate the difference between the two, and that will be what your eccentric load is in either axis. What you can now do is you can now pattern the faces where the eccentricity loads are applied, thus giving you a set of more critical results. So in this example over here, we have a series of columns. Some of these columns are supporting pinned beams. If I just go into this view here, we can see that some of these columns are supporting pinned beams. So say for example, these four beams I'm hovering over are pinned, being supported by this column over here. We can also see, if I just turn on the imposed load case, we can see that there's imposed loads applied to both floors, hence some of these beams are going to be subject to imposed loads. I'm now going to perform a gravity design. And we can review either the analysis or design results, but in this case, what I'm going to do, I'm just going to review the analysis results as the effects are more easily seen here. If I go into Open Load Analysis view, make sure I have a combination selected. So in this case, I performed only gravity design, so I only need one of the gravity combinations. And if you review the results in either the major or the minor axis, you can see when viewing the analysis diagrams that one of the diagrams would have a dotted line. The dotted line over here indicates the eccentricity moment. If you see where this red line is, which you can click and drag to any location, or you can use the toggles at the top. I'm just going to use the toggles at the top to move that line to 4 meters, which is basically the top of the lowest stack. We can see that the moments, or the eccentricity moments at this location, are 4.5 kilonewton meters, and we can also see that by looking at the properties window over here. There are two things that need to be done to apply eccentric moments, or to pattern the eccentric moments, sorry. The first being under Home and Model Settings, expanding the loading tree in general. There are options over here for load patterns. We're just going to tick this second option, which is to use patterning of eccentric moments for steel columns. And the second is in the load ribbon. If we open the load cases window, under our imposed load, there's now a new column added to this window, which gives us the option to pattern eccentricity moments. So for any load that's set that has the type set as imposed, this option will appear, as it does for regular pattern loading. If I were to now perform the design again, and just set that to 0. So 0 being that no pattern's going to be applied. Now, if you remember from the slides what the patterns looked like previously, where no patterns were applied, the eccentric moment over here was 4.5 kilonewton meters, and at the top it was 0 kilonewton meters. If you now cycle through the patterns, say pattern 1, which is where faces A and B are loaded, or eccentrically, you can see that the eccentricity moment at the top is now minus 3.6, whereas previously it was 0. And that would be the same for pattern 4, as this column is loaded equally and with equal and opposite loading on both sides, or on all 4 sides. And if we look at pattern 2, we can see that where previously the moment was 4.5 kilonewton meters, now it's 6.3. Now the effects of these are simply that these eccentric moments get added to the original analysis moment, giving you the overall design moment. Now, I mentioned faces A, B, C and D and how to see them. You can see which faces are which by going into Scene Content, and if we look at the additional options under Members, there's a direction item which can be turned on, and if we turn on the direction arrow, we can see that if we zoom in, there's a pink arrow above all of the columns over here. Oh, sorry, to the side of all of the columns. These arrows are all located on face A. I'm just going to now look at the design results for this column over here. So this is the column that we previously looked at the eccentricity moments for. So if I turn on the results and have a look at moment major, the bottom stack for the same combination, we can see that if we have a look at the design moment over here of 6.3 kilonewton meters, it tells us over here when we're looking at the critical, the combination of the results that we're looking at, it tells us over here what the position of the maximum moment is and which pattern it's using. So it's telling us here that it's using eccentric pattern 2, which has given us the most critical result. And if we do the same at the top, you can see again it's given us pattern 2 as well. So the next feature we'll be looking at is minimum design forces. Now this feature is there just to simply aid with the efficiency of design and also looking at output results. It allows for flexibility and control of design forces, and this can be used when looking at connection resistance checks, beam end forces and foundation reactions, and it's activated using the design settings. The minimum design force is just simply a way to control the minimum forces that are used within the output. and there are also options to set rounding values for certain output types as well. So to demonstrate how the minimum design forces work, I'll be looking at foundation reactions, but as mentioned, the same thing can equally be done for beam end forces or connection resistance checks. In this model, I've performed a design of the model, and the results I'm going to be primarily really interested in are for combination 1, which is the gravity combination. If I go into the results view, and here I've got the vertical reactions turned on for this combination, we can see that the columns under the columns are giving us a certain reaction. Some columns are giving higher reactions than others. If we have a look over here, it'll rotate around slightly, we can see that there are a series of columns over here, say this column, C2, B1 and A1 are giving us reactions that are much smaller than the others. So in terms of minimum design forces, what we can do is we can go into the design ribbon and click on settings, and under design forces we can locate the minimum design forces over here for the different result types. So say over here you've got result types for things like your brace forces reporting, your beam end forces reporting, and also your foundation reactions reporting. So I'm just looking at foundation reactions reporting. There are a series of different force types which come in the form of axial forces, shears and moments in both the major and minor axes, where we can set a minimum force. Now what we can do is, if we don't want to see, if we want to see the smallest force, what we can do now is, if we want to say simplify some of these forces over here, say for these 3 columns that are subject to small forces, and I'll say hypothetically to a force of 150 kilonewtons. So any support that has a reaction of under 150 kilonewtons, if we just want it to display 150 kilonewtons in the report, we can just set this value over here, 150. I'll just keep it as 0 for now, just to show what the report would look like. And I'm just going to create a report, just to show here, for foundation reactions, showing just the first combination, the gravity combination, for every column in the structure. If we click on show report and have a look at the results, we can see that for A1, B1 and C2, we can see that the results are shown there are still the same results that we saw in this view over here. If I go back into the design settings and set this value to 150, what this will do is it will display any axial force below 150 kilonewtons as 150 kilonewtons within the report. If I just remember to update this report, we can see that for A1 now, the vertical support reaction is shown as 150, the same for B1 and the same for C2. So this just allows us to simplify the design forces. What we can also do is, if we have a look at some of these numbers over here, some of these numbers are very precise. However, if you have a look over here, say this force here being 362.7 kilonewtons, that there is the accurate result of what the support reaction at A2 is. I'll just show where A2 is, which is this column over here, 362.7 kilonewtons. What we can do is, in the design settings, is we can simplify that further by applying rounding values to forces. If I click on this option here showing rounding increment to force, it gives us a default value of 10 kilonewtons. So what that will do is it will round up by increments of 10 kilonewtons for all of our all of our force results. So this just won't do this for the vertical force, it will also do this for the horizontal forces as well. So you'll see for A2 where it's showing a major axis shear of minus 19.2, this will be rounded up as well. If we click OK and click update here, we can see that take effect. And what we can do is we can also do the same for moment rounding increments. So the default rounding increment is set as 5, but we could make that 10 as well. I'm just going to keep it at 5. We should see that 30.1 change now to 35. So the final topic I'll talk about is the pile punching shear check. So in the program, for the last few versions of Tekla Structural Designer, you could design foundations, including mat foundations. Within mat foundations, you could always design piled mats. One of the limitations previously for piled mats was that the punching shear check between the piles and the mat foundation could not be checked. So those checks usually had to be performed externally, either based on the pile capacity or the force in the piles. Now, the functionality of designing or checking punching shear between the pile and the mat foundation has been included within the program. It's important to understand that the punching shear resistance is assumed to be provided by the concrete alone, so there is no option to add specific punching shear reinforcement in the form of studs, rails, as you can do for columns which are supporting slabs or columns supported by mats. The check will consider analysis types such as the 3D building analyses, so first order or second order analyses, FE chase down and gorilla chase down for all active gravity, wind, seismic and response spectrum analysis combinations. This check only considers a single pile, so no pile pairs, and only vertical shear, so no moment, as piles are modelled as pin spring supports without any moment fixity. Just as punching checks of columns supported by piled mats, all loading and reactions from the ground bearing springs within the punching shear perimeter are considered. And it's also important to consider that the pile punching check is only available to Eurocode and US head codes. So in this example, we have a 3D model that has been designed. It's also important to understand that the slabs of the mat foundation has been designed, as we can see when we look at the slab mat design detailing. Not that the floor slabs are not designed, as in this example we're only interested in the mat foundation. Also, the pile capacity can be seen just simply by clicking on the piles option over here, pile status, and we can see that all of the piles within this model are passing. And we can just see the force in some of these piles simply by right-clicking on a pile, selecting check member, and we can see what the maximum force is within the pile and what its limit is as well. We can use ratio over here, and ratio will just allow us to see how hard each one of the piles are working, which is the same view I'm looking at when looking at the piles on plan. So when having a look at the piles on plan, we can see, looking at just using the legend on the left hand side over here, which piles are working the hardest. And the piles that are working the hardest are these piles that are shown in green over here, which are between 40 and 60% of their capacity. If I just select hypothetically arbitrarily this pile over here, we can see that it's working at about 360 kilonewtons, so just under half its capacity. Now, if we want to add a punching shear check between the mat foundation and the piles, all of that information is found under the foundations ribbon. So previously the foundation ribbon just ended over here, where you could add patches. Now there's an option of adding the punching check as well. If you hover over this, this is similar to the punching check that's here under the design ribbon. So this punching check here that's under the design ribbon applies to columns. This one over here under the foundation ribbon applies to mat foundations. If I were to click on this icon over here, it will give me an option of, it will give me a hint over here as to pick the pile punching location. I'll just pick this pile over here as an example, and we can perform a check just simply by clicking on design punching shear, and we can see that check's now been complete. I'm just going to turn off slab items in scene content, and the reason I turn off slab items is just to make it more visible to see the status of the pile punching check. We can also review the punching check simply by right-clicking over the punching check and selecting check punching shear, and we can see the checks that have taken place, so a check between the loaded and the control perimeter. We can just follow the exclamation mark over here to find the most critical result, and in this case it's the gravity combination under FE chase down conditions, and here's the design checks that have been performed. Now there are settings that can affect the pile punching shear check, and this is a way of just simply simplifying the settings. So if the pile's working at almost or close to its capacity, a quick way just to rationalize the checks would be to go into settings, and if we just expand the concrete tree, expand cast in place, foundations, mat foundations, and piles, there's this tick box over here to use the pile capacity for the pile punching check. If I tick this option over here and click OK, what this is going to do is, if I just open the pile catalog now, if we have a look at the pile resistances over here, so I've set the pile capacity for this pile here to be 800 kilonewtons. So what this will do is it will just use the 800 kilonewtons as the capacity for the check. If I now right click, select check punching shear, and if we have a look at the force that's being used, we can see that over here for the pile load, it's using either the maximum force in the pile. If I just double click to open this, move that across, we can see that it's using the maximum result from either the maximum force in the pile reaction, or the pile design compressive force, which is the one that I'd set within the window. So here it's just taken the highest of either the pile reaction of 352.5 or 800 and using that as the pile load for the punching check. You can see now when we have a look at the unreinforced shear ratio at the control perimeter, we can see it's working at very close to its capacity here. So to conclude today's webinar, there have been some more fixes, new features and enhancements that have not been included as part of this presentation. The reason that they've not been included is because they're not quite as relevant to the UK market as these features that I've demonstrated here. If you do wish to see more information on those, please do refer to the release notes. So to find the release notes, the easiest way to do that would be to go into download.tekla.com, locate Tekla Structural Designer, and if you locate the latest updates, click on Tekla Structural Designer at the top over here. So this is looking at the latest Tekla Structural Designer updates, and clicking on Release Notes, you'll find a lot of the information that I've spoken about on here to more detail, most of which I've spoken are under highlights, but you can also see some more information regarding other features and other enhancements as well. Should you have any further queries, you can always contact us at support. So you can either email us at tekla.support.uk@trimble.com, or you can call us on 0113 887 9790. Thank you for listening. We will now take questions. Any questions which do require further research or a longer answer will be sent to you in an email after this webinar on a later date.